Hey guys, welcome to your week 3 task 2, which is going to be an instructional video that's going to talk about pH and molarity. So as we get started, I would maybe pause this video and go get your copy of your task 3 practice problems, because we'll be going over these throughout this instructional video. And remember, if you don't have a printer, that's fine. You can just get and show your work on a separate sheet of paper. Okay, so let's go ahead and get started. Okay, so we're going to do a quick little review from last week. The idea of what is an acid versus what's a base. So we're, though, going to focus on, of course, pH. And so when we talk about pH, if we are less than 7, then we are considered an acid on that pH scale. And talking about a base, when we talk about a base, having a pH greater than 7 is going to make us basic. Okay, also just for review, remember the process of neutralization is a double replacement reaction where you mix an acid and a base, and that's going to come together and make an ionic compound and water. Remember, the hydroxide ion and that H+ ion come together to make good old H2O. Okay, so now when we talk about new content, so there are 2 ways that we can, and this should be a familiar word, quantify. So that word, once again, remember, means number. So there's 2 ways that we can put numbers to the strength of solutions, whether it's acidic or basic. And those 2 ways are either through assigning it a pH or something called molarity. Okay, so first we're going to talk about pH. Okay, so we're taking a really simple approach with pH. Honestly, most of this content you probably already know, and that the pH scale is a scale from 1 to 14. But that's just a scale. We still can have pH ranges outside of that range. And pH is also a logarithmic scale. Which if we were in class, we would have spent a little bit more time talking about this. But the fact it's a log scale, some of you guys in Algebra 2 have started doing things with logs and that mathematical concept. But this is the idea that when you take a jump on the pH scale, it's that idea of a base of 10. And so every time, like if you go from a pH of 1 to 2, that's a jump of 10. So with the pH scale, we know that any solution that has a pH less than 7 is going to be considered acidic, and any solution with a pH greater than 7 is going to be considered a base. Okay, so at this point, you should be able to go on your practice problems, defining acid and base, okay, bringing in some of the content from last week and being able to talk about those. Okay, honestly, we haven't done indicator yet. That's coming in just a little bit. But this is also where you can go ahead and define pH. And then we just went over the answer to question 2. So take some time and do those, and we'll come back to indicator in just a sec. Okay, so with this slide, I like this visual. You guys know how much I love the particle level. And so here we've got this idea of H+ ions being represented in red and hydroxide being represented in blue. And you can see here we have that pH scale with, we've got neutral in the middle, and then at the ends we've got the 0 and 1 and the 13 and 14. Okay, words that you may hear: acidic is something we would use to quantify something that is an acid, and then alkaline is the word we would use to talk about something that is basic. Now, the thing that I want to point out here, it's not that this side of the scale is where we would have hydroxide, or excuse me, not hydroxide, our H+ ion, and this side of the scale is where we would have the hydroxide ion. It's that even with bases, there still can be those protons or that H+ ion floating around in the solution. That the pH scale itself is just a way to quantify the total number of H+s in the solution. And that is why it's called the pH scale. This H is literally representing that H+ ion. Okay, so even if we're up here at bases, there still can be H plus ions in the solution. There's just not going to be very many. Whereas if we're down here at the acidic range, that's where we're going to have way more of those ions present. Okay, and just pointing this out, if we're at neutral and we're at a pH of 7, like pure distilled water, that is where the H plus ions are going to equal our hydroxide ions. We'll have the same amount of both in the solution. Okay, and this also gives a great representation of pHs of a lot of different stuff. Okay, getting all the way up here to milk and magnesium. You guys saw that in your demos last week and how it would align on the basic side. Okay, seawater, that's kind of interesting. Some people wouldn't realize that seawater is basic, but seawater is becoming more acidic through ocean acidification, okay, which can create a lot of problems. And then we have things down here like lemon juice. Lemon juice is pretty acidic. This is why lemon juice, the acid that's in lemon juice is citric acid. And if you look at any sour candy, like Sour Patch Kids or like Warheads, one of the main ingredients is citric acid, and that's what gives those candies that sour taste. And so, you know, if you eat too many of those candies, you actually can burn your tongue, and you're basically having the same thing happen about what we talk about, where if you get hydrochloric acid on your skin, that it can burn your skin. Well, you can burn your tongue if you eat too much sour candy. Okay, now just talking about a real live process with pH and digestion. So you guys know that digestion is the process by which foods are broken down into simpler substances. So there's some different types of digestion. First off, we have mechanical digestion, and mechanical digestion is what happens in your mouth, like the physical process of your teeth tearing apart the food. Well, then down in your stomach, we have chemical digestion that happens. And this is where pH comes into this, because the gastric juices are very acidic, and that we can use those acidic solutions to chemically break down those large molecules into smaller ones. And this chemical digestion happens in your stomach and small intestines. Okay, so here are some pH ranges I want you to kind of pay attention to. So your mouth has a pH of around 7, and your saliva contains different enzymes which start the breakdown process of things like carbohydrates. And then, of course, we know that after the food enters your mouth, it's going to go down into your stomach. Okay, and in your stomach, we have a very, very low pH. Okay, and at this point, this is where things like proteins get broken down into smaller amino acids. And so we go from neutral all the way down to acidic in our stomach. Okay, then in our small intestines have a pH range of about 8. Okay, so almost would be considered a little basic. And this, for the most part, is where digestion ends. It's just, at this point, we have to have the pH get back up to around neutral in order for those nutrients to pass into our bloodstream. Okay, and the other thing that I want to point out with this, if any of you have any little brothers and sisters, or you've babysat, and the idea of diaper rash. Diaper rash is something that can happen with small children where the pH of their poop doesn't come back up to around 8 and actually can burn their skin. And so when we see something like diaper rash, it's not the diaper giving them the rash, it's the pH of their poop that actually is burning their butt, because it actually goes through their system too fast to where in the small intestines the pH isn't brought back up to a safe level. So that idea of diaper rash, you can sound really smart, but it's not diaper rash. It should really be called acidic poop burn instead of diaper rash. Okay, so here's a list of a whole bunch of different indicator solutions. So guys, if we were in class right now, I would pull out bottles of all of these, and I'd have some things that were acids and some things that were bases, and we would make lots of different colors. But every single one of these off here to the side is a different pH indicator. That these are substances that will change color based on the acidity of the solution. So some of my favorite, I had a really cool demo with Congo Red. Okay, Congo Red, if it's an acid, is blue, and if it's a base, it's red in color. And so it's really interesting. I have this sponge at school that's red. Okay, so imagine a red sponge. And I dip it into a red solution. But then when I pull the sponge out, it turns blue. And that's because that red solution that I put it in, I also added some acid to it. And even though the solution is red and you would think that the sponge would soak up the color red, it actually changes to blue because the sponge is also soaked in that indicator. It's kind of a fun demo. And then the same thing. Then I take and rinse the sponge out, and part of the sponge is still a dark blue, and then I dip it into a blue solution, but the blue solution is really a base, which then turns that sponge back red. So it's kind of a mind game, but it's a pretty cool demo. Another one that we actually have used in class is bromothymol blue. I don't know if you guys remember, but with our demos on properties of ionic versus molecular compounds, we were trying to figure out if carbon dioxide could dissolve in water. Okay, and carbon dioxide, you guys know, is CO2. Okay, and when carbon dioxide dissolves in water, it actually forms an acidic solution. And so, if you guys remember, we just had a beaker of distilled water, and it was green in color because I had put some bromothymol blue in it. And then as more CO2 it was just like blowing bubbles in chocolate milk. It actually took that solution from this bluish green color into the acidic range. Okay, another one that's very common is phenolphthalein. I use that a lot too, especially when I have leftover things from labs or demos that are acidic or basic. I'll use phenolphthalein. Okay, so indicators are solutions that help indicate the pH of the solution. Imagine that. Its definition is almost in its name. On the demos last week, you guys saw both demos used universal indicator. And I have a ton of this back in the classroom. And once again, what's cool about the universal indicator is it does give us that rainbow color effect. And you guys saw that in the rainbow tube demo. Okay, but there's other ways to indicate pH too. We have a set of pH probes in the classroom. So this would just be a digital, just like a thermometer versus a digital thermometer. To really quickly tell the pH of a system. And then we also have things called like pH paper, where you can put that piece of paper in a solution and the color would then indicate what the pH is. So this pH paper is actually soaked in an indicator, and just like a couple slides ago, all those different colors that different indicators can do, there's a lot of different pH paper that you could buy to change colors based on the pH of the solution. Okay, if any of you guys have a little brothers and sisters are at home, this is pretty cool. If you get purple cabbage, okay, and you cut that cabbage up just a little bit, place it in some water and boil it for a couple minutes, and then you strain off the water, that purplish color water, that now has some of the dye that kind of gives the red cabbage its color. It is actually a natural pH indicator, which is super cool. So it's that purple color when it's pretty neutral. If you add something acidic to it, like lemon juice, you can get it to turn a really pretty pink color. Then if you add something basic to it, like mini cleaners, it'll turn green or yellow. Something like drain cleaner added to the cabbage juice or bleach actually turns it clear. And that's because drain cleaner and bleach have bleach in it, and it actually bleaches the color of this dye out. So this is a pretty cool little experiment you could do. You could go and Google search Red Cabbage Lab. If any of you are also taking on the role of maybe helping younger brothers and sisters with this online learning, this is pretty cool, pretty easy to do at home too. Okay, and at this point you can go back and put the definition of an indicator down on your practice problems. Okay, so once again, remember that there's two ways that pH can be quantified, pH and molarity. So now we're going to talk about molarity. This is a brand new concept. Okay, molarity kind of has the word mole in it, so we're going to be talking about moles when it comes to molarity. Okay, and remember that mole is the unit in chemistry that allows us to count at the atomic level. Okay, so the first thing we want to talk about with molarity is you need to associate the word molarity with the word concentration. Okay, so here's an example. Hydrochloric acid on the pH scale is going to have a pH of about 0. Okay? And with different concentrations of hydrochloric acid, 0.1 is going to be not very concentrated hydrochloric acid versus 12 molar hydrochloric acid is very, very concentrated hydrochloric acid. And once again, concentration has to do with how much is dissolved in a certain quantity of water. And so understand that the pH of hydrochloric acid is always going to be really, really, really low. But we can have a wide range of molarities from 12 mole all the way to 0.1 mole. That's going to represent the concentration of that solution. Okay, so an acid or base's strength could also be talked about with the word molarity. So think concentration or strength. Okay, so here's just our classic definition and key concept for molarity. Molarity is a measure of the concentration in terms of moles. Okay, so there's where we get that molarity. It's because moles is part of this. Per liter of water. Okay, so there's our amount. We're going to be doing this in liters. Okay, and so here's the equation that we'll use to determine the molarity of a solution. Moles of solute divided by liters of solution. Okay, and let's take a second and go back and talk about this. Liters of solution is going to be talking about how many liters of water we have. Okay, and the moles of the solute, once again going back to stuff that we talked about earlier this year, is the thing that's being dissolved. Okay, so how many grams of something do you dissolve in a certain amount of liters of water? We could then determine molarity if we go from grams to moles through the conversion factor of molar mass. Okay, so molarity can be expressed and is expressed with a capital M, that's its unit. And it can also be seen as a conversion factor, some number of moles per 1 liter of solution. Okay, and honestly, for a chemist, molarity has a much wider range of application than pH does. Okay, so question 3 on your practice problems is it just wants a definition of molarity. Okay, so let's go ahead and take a second and do that. You can go back to the last slide and copy that key concept. Okay, and the other thing I want to point out is this is the back of the periodic table that we use in regular chem. Okay, honors chem, you guys are going to need to go look at your reference sheet and see if molarity is listed on there. If it's not listed on there, on the AP exam, this is an equation that you would have to have memorized. Okay, but here is our equation. It doesn't say molarity, it says concentration. Remember, concentration is what molarity is. And once again, we see capital M, our units for molarity. And you guys have seen that in class, like with labs we've done, you've seen things like that say like 3, and it was a capital M, 3 molar HCl. That literally tells you that it's hydrochloric acid, but it's at a concentration of 3 moles of that hydrochloric acid dissolved in 1 liter of solution. Okay, so you guys have this equation that you'll be able to use. Okay, so the skill we're going to be talking about with you guys is how to do molarity calculations. Okay, so let's go ahead and read through what we have here. This says, what is the molarity of 0.5 liters of solution containing 0.5 moles of sodium chloride? Okay, so remember our equation is molarity equals moles over liters of solution. Okay, so here if we plug in our numbers, we've got 0.5 moles of sodium chloride over 0.5 liters of solution. So that means that our answer to this problem, 0.5 divided by 0.5 liters, is going to be that this would have a molarity of 1. Oops, changed my thing. Okay, so this would be a 1 molar solution of sodium chloride. Okay, let me switch back to my pencil here. Okay, next question. How many moles of H2SO4, so that's sulfuric acid, are present in 0.5 liters of a 0.9 molar solution? Okay, so here we have a little bit more, we have some different information. We have 0.9 molarity is equal to some number of moles over 1.5 liters. So this question isn't asking us to actually solve for molarity. It wants to know, I need a 0.9 molar solution. How many moles do I have to dissolve in 1.5 liters? So here you guys could isolate your variable, right, on the top of this equation. This could be looked at as your x, and through algebra you can move 0.15 liters to the other side of the equation and solve for this. So if we were to do this algebraically, we would want to get x by itself. Well, x is in the numerator, so that means we have to times both sides by 0.15 liters. And then we would be able to solve for x. Okay, there is one other way that we can solve this problem that I'm going to show you on the next slide. Okay, so here's that same question. How many moles of H2SO4 are present in 1.5 liters of a 0.9 molar solution? Okay, so you saw how to solve this just using the equation. Okay, well, if you can remember that molarity is a conversion factor, okay? And remember that it's moles over liters, so let's turn this into a fraction. That would mean 0.9 moles has to be equivalent to 1 liter, because these units, moles over liters, is molarity. So that means we now have a conversion factor. 0.9 moles is equal to 1 liter. Okay, so now if we just go through dimensional analysis, this question's asking for how many moles are equal to 1.5 liters of solution. Okay, so now we can actually use molarity as a conversion factor. We've got liters on top, so that means liters has to go on the bottom. So that means 1 liter would go on the bottom, and 0.9 moles would go on top. Liters would cancel. We'd be left with the units moles, which is what this question is asking us for. And now all we have to do is plug this into our calculator. Okay, so I plugged that in and I got 1.35 moles would be our answer there. Okay, so I've showed you two different questions. One where it asks for you to solve for molarity, and another question where it asks you to solve for moles. Okay, and there's some different ways that mathematically you can get those answers. Okay, now let's look and see what you guys have to do on practice problems. Okay, so here's those last 5 questions on the practice problems. All of these are going to be calculations. So let's kind of just read through these. Okay, it says, what is the molarity of a solution if you are given moles and liters? So you're given moles and liters, so you should be able to just plug that into the equation. Moles divided by liters. Okay, that looks like the same for question 5. It's asking for what's the molarity. Are given moles and liters. Same with 6. 6 is going to be the same thing. What's the molarity? And you're given liters and moles. Okay? However, number 7 is a little bit different. Number 7 wants to know how many moles. So in this particular one, this is where you can follow the example that I just solved 2 different ways. The last question on the previous 2 slides was trying to solve for moles. Okay, so you can either use molarity as a conversion factor, which would look like this. 0.954 moles is equal to 1 liter. Right? Because we could change these units out. And remember, moles is a conversion factor, moles per liter. Okay? And you can use that to solve for it, or you can plug it into the equation and try to solve for it algebraically. Okay, and the very last question, we haven't done one like this at all. Okay? So this one says, what's the volume? So once again, you can use algebra and plug your molarity and your number of moles in and solve for liters as your x. Or once again, you can use this molarity right here and write that as a conversion factor. 0.25 moles is equal to 1 liter. Hey guys, this should be moles up here, sorry. Okay, don't abbreviate. You guys know I yelled at you in class for this. Don't use a little m for moles. You have to write out MOL. Okay, so you could use this as a conversion factor, and once again, set this problem up. I'm going to come right up here so I have space. How many liters is equal to 0.55 moles? And now plug in this conversion factor correctly to solve for your unknown. Okay, so good luck solving question 4, 5, 6, and 7, and then 8. Okay, so kind of wrapping up acid and bases. Could you guys answer this question? What ion is responsible for acidic solution? That should be a question that you would know the answer to. Okay, also the idea of what ion is responsible for a basic solution. You should be able to answer this question at this point. Okay, and then with practice, finishing up your practice problems, understanding that molarity could be a general conversion factor, or what is the equation for molarity is a question you should be able to answer. And then last but not least, what are the products of an acid-base reaction, and maybe even being able to identify what type of reaction that is. Okay, and good luck finishing up your practice problems, and I'll talk to you guys in a little bit.